This work is called Learning a Single Neuron with Gradient Methods, and this is a joint work with my advisor, Ohad Shamir. So the question we asked ourselves in this work is, before analyzing deep neural networks with complex architectures, do we really fully understand even the most simple neural network, non-linear neural network we can think of? And I think the simplest neural network we can think of is such that it consists of only one single neuron. So we consider this fundamental problem of learning a single neuron and in the realizable setting. This boils down to minimizing the following function f of w, and here sigma is the activation function, it's some nonlinear function from R to R, d is some distribution over vectors in Rd, v is a fixed target vector, and the learned vector w is randomly initialized at the beginning. In our case, we initialize it from standard Gaussian initialization, standard Gaussian distribution. So the question we ask ourselves is, can we minimize this f of w using gradient-based methods? And by gradient-based methods, we mean gradient descent or stochastic gradient descent or its continuous variant gradient flow. The main results we show in this paper are that first, in order to ensure convergence, we actually need non-trivial assumptions on both the activation function and the input distribution. So non-trivial assumptions on just one of them is not enough in order to ensure convergence. We show that under some mild assumptions on both of them, we can show convergence, at least in constant probability, for all the gradient-based methods I mentioned before. And if we allow ourselves to have stronger assumptions, namely that the distribution is spherically symmetric, we can show convergence with high probability. Okay, there are a couple of previous results studying the problem of learning a single neuron. First, there are a couple of results about learning a single neuron using other algorithms, such as, for example, the isotron algorithm. But these algorithms are not widely used today in learning neural networks. There are positive results for strictly monotonic activations, but these activations usually do not include the standard activation people use today, such as ReLU. There are specific results for the ReLU activation and standard Gaussian input distribution. However, the analysis for these results crucially depends on initializing the learned vector W at the origin, instead of using standard random initialization, such as initializing it from a standard Gaussian distribution. And there is a result that shows constant probability convergence, specifically for the ReLU activation, and it requires some technical condition on the eigenvalue values of a certain distribution-specific distribution-dependent metric. Okay, let's start with some negative results. First, we show that even for some nice distribution, convergence might be hopeless, even if we use the ReLU activation function. So assume that the activation is ReLU, and we use a distribution which is uniform over the vectors EI, that's just unit vectors, where EI equals to 1 at the ith coordinate and 0 everywhere else. And the target vector is just a vector where each coordinate equals to 1 over square root of d. That's just a norm1 vector. So what happens here is that if we initialize W from standard Gaussian distribution, then the gradient of f of W will look something like this. And the problem here is that each summand of the gradient is multiplied by the indicator function of whether W times the vector EI is larger than 0. So we can show that actually with high probability, actually with exponentially high probability, at least omega d of the coordinates of this gradient will be 0. This means that at least omega d of the coordinates, these coordinates for which the gradient is zero, so the coordinates of W will remain the same, will remain unchanged from their initial value. This means that we will not be able to learn the target vector V, at least in these coordinates. So for this distribution, convergence is actually hopeless. Next, we'll show that for some nice Lifshitz activation functions, we will also may not be able to converge, even if we use standard Gaussian distribution. So assume that sigma, the activation function, is some periodic function and one Lifshitz. For example, we can choose sigma to be sine of x or cosine of x, and the input distribution is just standard Gaussian. By reduction from a previous work by Shamir, we can show that the variance of the gradient of f of w, where we take the variance with respect to the target vector b, is exponentially small. Exponentially small in the input dimension. The corollary of that is that under the above assumptions that sigma is periodic and the input distribution is standard Gaussian, actually the gradient is virtually independent of the target vector v. So this means that in a sense W will not be able to learn the target vector because the gradient is just independent of any target vector. And I'll just mention that the above actually applies for a very large family of distributions, roughly distributions with Gaussian tail. Okay, so after we showed some negative results, what can we say about what are the assumptions that we do need in order to ensure convergence? So the first assumption is about the activation function, and the assumption is that we need some kind of weak monotonicity for the activation. So in the negative result, it was a periodic function, which is a very non-monotonic function. So if we have the following assumption that sigma is monotonic, non-decreasing, and it satisfies that its derivative, at least close to zero, is larger than some number, than some constant gamma. So this assumption includes almost all standard activation function we can think of, including ReLU, leaky ReLU, hyperbolic tangents, or sigmoid. So it includes most of the activation functions people usually use. The assumption about the distribution is the following. Want the input distribution to satisfy that for any two target vectors, W and V, if we take dWV, which is the marginal distribution of the span of W and V, then the density function of this marginal distribution will have some positive concentration, at least around the origin. So to give some intuition about this distributional assumption is that we need the distribution to be sufficiently spread at least around the origin, but in every two-dimensional direction. So this assumption holds for example, for standard Gaussian distribution, or a mix of Gaussians, and it will also hold for any distribution if we mix it a little bit by standard Gaussian distribution. So it actually holds many different distributions, and it just means that the distribution is sufficiently spread around the origin. Okay, what can we show under these mild assumptions? The first theorem we show is that the gradient, in a sense, points in a good direction. So under the previous assumptions, if the angle between W and V is smaller than some pi minus delta, then the gradient of f of W times the direction of W minus V, which is the direction that we want to move towards, is larger than O of delta times the distance between W and V. So in a sense, it means that if the angle between the vectors is not close to pi, then gradient will point in the direction that it should point to, which is in the direction of the minimum. Okay, using this theorem, we can now show that we have convergence for a single neuron, at least with constant probability. So under the previous assumptions, if we initialize W, where the distance between W0, W at initialization at V is smaller than 1, then there is some constant lambda, such that for a sufficiently small learning rate eta, if we run gradient descent for t iterations, then the distance between Wt and V will be smaller than W at initialization, and then the distance between W at initialization and V times 1 minus eta times lambda to the power of t. This is linear convergence, and the reason that we say that this is with constant probability is that the assumption that the distance at initialization between W0 and V is smaller than 1, so this assumption holds in constant probability, at least with respect to certain initializations of W. I will just say that the main technical difficulty in applying the first theorem to show the convergence theorem is ensuring that the angle remains bounded away from pi. And actually, if the angle is exactly pi, we cannot show that the first theorem holds, and we cannot actually ensure convergence. Okay, let's move on to some stronger assumptions. Let's say that in addition to the previous assumptions, we also would assume that sigma is the ReLU function. So that's just sigma of x is the maximum between 0 and x. And let's say that D is a spherically symmetric distribution. This includes, for example, standard Gaussian distribution or a uniform distribution over the unit ball and many other distributions. So under these distributions, we can show that gradient descent will converge with high probability. And we say with high probability over the initialization of W. So it means that for almost all initialization of W, we can ensure convergence of a single neuron. And the key observation in this theorem is that if the distribution is spherically symmetric, then the angle between the target vector and the learned vector can only decrease over time. So if we think about gradient descent, that at every iteration of gradient descent, the angle between W and V can only decrease. So the distance between them can only get smaller over time. We can ask ourselves if this is a phenomenon that happened for only a spherically symmetric distribution, or it's some general property of learning a single neuron. And actually, this is something that is specific for spherically symmetric distribution. In order to show it, let's assume that the input distribution is Gaussian distribution with unit variance, but the mean not at the origin, but at the vector 1, 0. So that's almost at the origin. And let's assume that the activation function is the ReLU activation. So in this case, actually the angle does not have a monotonic behavior. So in the left, we see the trajectory of gradient descent from different initializations, and we see that the angle between the target vector, which is marked by a red cross, and the trajectory, so the angle between them does not monotonically decrease. And in the right side, we can see the angle with respect to every iteration, and actually the angle achieves any value between 0 and pi, so it doesn't monotonically decreases. Okay, let's wrap it up. So what we showed is that even for the simplest neural network consisting of a single neuron, convergence analysis can be actually extremely difficult. We need assumptions of both the input distribution and the activation functions, otherwise we cannot ensure convergence. we showed that under sufficiently spread distributions and with the weakly monotonic assumption on the activation function, convergence is guaranteed, at least with constant probability over the initialization. We show that under spherically symmetric input distributions, convergence is guaranteed with high probability, but this is only because of the monotonic behavior of the angle. This behavior does not generalize to even slightly non-symmetric distributions. And an interesting future research direction will be to show that we can achieve convergence for a single neuron with high probability, but for general distributions which are not symmetric. That is it. Thank you very much.